Hello everyone, this is Mr. Teen Tutor here, and today we will be talking about vector functions. As you can see, this is a multivariable calculus topic. We have an x component right here, a y component, and a z component. We have two questions on the table today. The first question is, what is the limit of this vector function as t approaches 1? And the second question is r of t continuous at t equals 1? This problem might seem daunting at first, but it really isn't, because in order to solve this problem, you will be using Calculus 1 and 2 rules and concepts. As I said, we have an x component, a y component, and a z component. In fact, these are functions within this vector function as a whole. So if we look at the x component, let's call this f of t. We'll call this g of t. And we'll call this one h of t. So again, the question is, what is the limit of this vector function as t goes to 1? What this actually saying is, what is the limit as t goes to 1 of each individual function within this overall vector function here? So what we are essentially doing is we are finding the limit as t goes to 1 of f of t, which again is the x function, the limit as t goes to 1 of g of t, which is the y function, and lastly the limit as t goes to 1 of h of t, which is the z function. So let's get to it. Let's start with the x function. So the limit as t approaches 1 of t squared minus t over t minus 1. When it comes to limits, you want to plug in the value and see what happens. So when we plug in 1, we get 0 over 0. But if you remember, you learned in Calculus 1 and 2 various techniques in order to get around that. So if we look at the numerator right here, we will notice that each term has a t in it. So let's factor out a t. So in the numerator, then I get t times the quantity t minus 1 over t minus 1. The t minus 1's cancel, and so I'm left with t, and I plug in 1. Then the limit of the x component becomes 1. Now let's shift over to the y component. So here we have the limit as t approaches 1 of the square root of t plus 8. Plug in 1, and we don't have to do much work. We get the square root of 9, which is 3. Let's shift here. We have now the limit as t approaches 1 of sine pi t over the ln of t. Let's plug in 1, and when we do that, we get 0 over 0. Unlike this example right here, we can't factor anything in order to cancel. Instead, we need to use L'Hopital's rule, which hopefully you learned in your Calculus 1 or Calculus 2 class. So with L'Hopital's rule, it states that whenever you get an indeterminate form from a limit, such as 0 over 0, we had to take the derivative of the numerator and the derivative of the denominator and plug in the value and test again. So let's do exactly that. So remember, we're using chain rule here. So this would be cosine of pi t times pi. So again, the numerator would be pi times the cosine of pi t over the derivative of the denominator. And hopefully you remember, the derivative of ln of t is 1 over t. So let's test again. Let's plug in 1 for t. When we plug in 1 here, we get the cosine of pi, which is negative 1. Negative 1 times pi is negative pi. And when I plug in 1 here, 1 over 1 is 1. So therefore, the limit of the z function here is negative pi. Now there are two ways you can express this. You can express this in algebraic form, which is this form right here with the brackets, or component form, which is the one with I, j, and k. So here's how you would write it in algebraic form. And here's how you would write it in component form. Unlike calculus 2 in 2D, when you found the limit of a function such as this, it would just be a number, or would be does not exist. In Calc 3, when we're dealing with these vector functions, the limit happens to be a vector. It's not a vector function because, as you can see here, there are no t's. We have actual concrete values. But it's a vector instead of just being 1 or 3 or negative pi, which is the case in 2D. Now let's shift to the second question. So the second question is r of t continuous at t equals 1? Let's first think about the definition of continuity in 2D. If you remember, there were 3 conditions. The first condition is the limit as x approaches c for f of x has to exist. The second condition is f of c exists. And lastly, the third condition, the most important of the 3, is that the limit as x approaches c of f of x equals f of c. So in this context, in 3D, the definition is very similar. In fact, this is the definition. In order for r of t to be continuous at t equals a, the limit as t approaches a for r of t has to equal r of a. And if you think about it, this makes a lot of sense, and it is very similar to condition 3 right here. So we computed the limit function in part 1. We got 1, 3, negative pi. So now we need to find r of 1. But if you remember, when we were finding the limits of each component, r of 1 did not exist for the x component or the z component. It existed for the y component because that became 3, but as you can see right here, we had t squared minus t over t minus 1, and when we plugged in 1, it did not work out. And the same thing with the z function here, where it was sine pi of t over ln of t. So the other condition of this is each component has to be defined at t equals a. And that is not the case with this one. As I just said, it is undefined for the x function here, and it is undefined for the z function here. That doesn't work out, so therefore the answer is no. Alright, so I hope you guys understand how this function works out. As you can see, it's really a matter of remembering your calculus 1 and 2 rules and concepts. It's just simply putting this into 3D, but you use those concepts in order to solve the problems. Alright, I hope this video helped you, and thank you very much.